Hello, my name is Kevin McLemore, and today I'll be doing a critical review on the primary source titled 2D Cosy NMR Spectroscopy as a Quantitative Tool in Biological Matrices. This application will be looking at cyclodexane. To get started, let's look at a little background. 2D Cosy NMR Spectroscopy, or known as correlation spectroscopy, is a technique used to study the interaction between nuclear spin in a molecule. The 2D Cosy technique involved the application of two radio frequency pulses separated by a short time interval. This creates a cross peak in the spectrum. These cross peaks provide information about the coupling between the spin and the molecule and can be used to determine the structural connectivity of the atoms in the molecule. Essentially, 2D Cosy NMR spectroscopy provide a map of the correlation between the spin in the molecule, allowing researchers to identify and study certain chemical groups and determine their relative position in the molecule. The main advantage of 2D NMR spectroscopy compared to 1D spectroscopy is that it uncovers signals that are overlapping in 1D spectroscopy due to similar resonant frequencies. Next, let's look at the summary of the study. The study aimed to evaluate the effectiveness of 2D NMR spectroscopy as a quantitative tool in biological matrices. The material used was cyclodextrin, which are used in the pharmaceutical excipients. The major findings were that 2D spectroscopy can accurately quantify cyclodextrin in biological matrices without complex sample pretreatments. The report did lack information on the limitations and potential errors of the 2D NMR spectroscopy method used. The next experiment could be to validate this method on other pharmaceutical compounds and not just cyclodextrin. For method development, the researchers first identified the signal of interest for hydroxypropyl beta cyclodextrin using a protein NMR in water, which was the widest signal at 1.1 parts per million. This corresponds with the methyl group of the hydroxypropyl group. However, this signal overlapped with signal from lipids and protein and plasma, making it unsuitable for quantitative using 1D NMR. Therefore, the researchers used 2D NMR spectroscopy to analyze the cross-peak interaction between the 1.1 parts per million signal and the central cavity of this cyclodextrin. This approach allowed for determination of 2D hydroxypropyl beta cyclodextrin amount without interference from lipids or protein and plasma. So we already know the compound of interest is cyclodextrin. So this cyclodextrin compound here at 1.1 parts per million, we are looking at the methyl group, and when a protein NMR is done, this is the spectrum here. This was spiked with a 2-hydroxypropyl beta cyclodextrin, and we can see the doublet peak of that methyl group coming off here. Here we have two NMR spectrum of cyclodextrin at different concentration. Right here, we have the NMR spectrum of 2D hydroxypropyl beta cyclodextrin at 1.1, and right here you see the methyl group, and at 1.1 around this region you can kind of see how it's getting overcrowded, and over to the right it's at 0.15 concentration, and again at about 1.1 you kind of see it start to get crowded and overlapping. So we've been saying that the main advantage of 2D spectroscopy compared to 1D spectroscopy is that it has the ability to uncover signals that are overlapping in 1D NMR spectroscopy due to similar resident frequencies. Here you have two 2D NMR spectrum. So the 2D NMR spectrum is of 2-hydropropyl beta cyclodextran and plasma at a concentration of 0.112. Right here at the correlation spot here between the methyl and the hydroxyl propyl group at 1.1 parts per million, and the protein H3 of the cyclodextran central cavity at 4 parts per million, this region here. Now, if we look over here to the right, this highlighted part, the square highlighted the absence of interference in this spectral zone. So this is how 2D spectroscopy have the ability to uncover peaks that are overlapping in 1D. Here you can see the overlapping of the 2D hydroxyl propyl beta cyclodextran with a compound used as a spiking solution, interfering with the methyl group with the same spiking solution used in the 2D NMR spectroscopy. You can see the interference here, and when you go to the 2D spectroscopy, you don't see that same interference. So how do we know this method is valid? To validate and qualify this method, researchers undertook a validation process to identify the most appropriate linear regression model, considering the influence of the molecular substitution of the hydroxyl propyl beta cyclodextran on the signal intensities and integrations. The study demonstrated the potential of 2D NMR spectroscopy as a valuable and accurate analytical technique for the qualifying of pharmaceutical compounds, including hardly detecting compounds such as cyclodextran and complex biological matrices without the need for complex sample pretreatment. Here you see the regression line. On this side, you have pre-calculated regression points at different concentration, and here you have the points where the concentration was increased and the samples were actually analyzed, and you come up with this regression line here. So what did we learn from this study, and what can we take from it? Well, we know from this study that 2D NMR spectroscopy can accurately quantify cyclodextran and biological matrices without complex sample pretreatment. We also know from this study that traditional 1D protein NMR spectroscopy was not effective due to overlapping signal and the spectra. And the study also tells us that cyclodextrans are ideal candidates for NMR analysis due to their uncertainty and molecular weight, making them difficult to quantify using traditional techniques such as LCs and mass specs. We know that 2D NMR spectroscopy is good for identifying molecules that overlap in 1D spectroscopy, but this report lacks information on the potential errors and limitation of 2D spectroscopy method use. The report did not discuss the effect of biological matrices interference on the accuracy of the method. For future experiments, we can look at validating this method on other pharmaceutical compounds and its excipients. The potential errors and limitation of method should be investigated to ensure the accuracy of the results. Future experiment could look at the effects of biological matrices interference on the accuracy of the method should also be a consideration. To wrap it up, 2D NMR spectroscopy is an effective quantitative tool for the analysis of pharmaceutical compounds and biological matrices. This method can accurately quantify cyclodextrin without complex sample pretreatment. However, more research is needed to fully understand the limitation and potential errors of this method and to validate its use on other pharmaceutical compounds. Once again, the primary source was 2D Cosy NMR spectroscopy as a quantitative tool in biological matrix application to cyclodextrin. The reference is seen below here. Once again, I'd like to thank you for your time, and if you have any questions, just reach out and ask me. Thanks.